So we are recording now, and if you're not interested in speaking, please just, if you're not interested in being recorded, please just don't speak up. Send me a message in the chat. Chapter 4, this deals with equilibrium, right? Equilibrium. So far in this course, we've been solving for resultants, and resultants were one force that represented all of the forces, and we used the forces, sum of the forces in the x equal rx, and sum of the forces in the y equals ry, and then we use those two components to find the resultant. Well, in chapter 4, equilibrium, what that means is three things are true. The sum of the forces in the x equals 0, the sum of the forces in the y equal to 0, and the sum of the moments are equal to 0. Equilibrium means everything cancels out. So what we're going to be solving for in chapter 4 is we're going to be solving for forces that cause equilibrium. Find the missing forces is what we're solving for here. And every single one of our forces, or every single one of our situations, is going to be set equal to 0. So we're always going to be using our equation equal to 0 in solving for our missing forces. Three force systems. We have concurrent force systems, remember? Concurrent, and that's all the forces going through one point. Concurrent force systems use just the first two. Parallel, we'll just use most of the time y in the moments. And then non-concurrent, they'll use all three. So for each individual force system, we're going to be using different equations. When we're doing these problems, what we need to do is we are going to need to find or draw what we call free body diagrams. That's essentially what we have been drawing so far, right? Forces acting on an object. But there are a couple different, in the pictures, you're going to see a couple different things that you're going to need to know how to represent. A triangle is a pin or a hinge. So if you see a force on a triangle, right, like this, that's telling you at this point right here, it's going to be hinged or pinned. So this thing only allows rotation. It does not allow motion in the x or the y, right? The board can't move up and down, the board can't move left and right because it's either pinned or hinged. It's also considered a knifed edge, and that keeps it moving because of the friction between the two things, the knifed edge and the board. So whenever you're drawing a free body diagram with a pin, a hinge, a knifed edge, what you want to do is you're going to represent it with an x force and a y force. So you would say px for the pin, py for the pin. And this will make more sense as we do problems. So that's the pin or a knifed edge. Another one is a roller. Rollers are represented with circles. Now, a roller does not provide support in the x, right? This board can slide back and forth on the roller. It can also rotate. What it does do is provide support in the vertical. It does not provide support horizontally, right? It's no resistance to lifting this board up. The only support it provides is upward support. That's it. So when you have a roller, right, that gets represented with an arrow that is perpendicular to the surface. So if I have an object like this, and there's a roller here, and it's up against an inclined plane, right? The way we would draw this in our free body diagram is we would draw a perpendicular force, where this is perpendicular to the inclined plane. So our roller in that case is only providing support perpendicular to the inclined plane, or to the surface that the roller is resting on. The final one that we're going to be looking at is known as the normal force. The normal force is a perpendicular, just like a roller, always perpendicular to the plane or the surface, whatever you want to call it. So if you have something at rest, let's say a circle is at rest on a surface, right? This circle can move left and right. It can roll either direction, but it can't go down. So it's going to have a weight going downward. That's its weight. And the force of the surface is going to be pushing back. That's known as the normal force. The source, it's the force of the surface on an object. It's always and again, all of these are on page 64 in your textbook. It's a good refresher as you're going through problems when you see something, just to check it out. But for today, we're just going to be dealing with normal forces and tension forces. Whenever you see the word tension, that's a pulling force. So if there's a cable holding something to the ceiling, right? Let's say this is a cable. Cables can only provide tension. So it has to be pulling, right? And that's important for your quadrant, because you have to be a second quadrant. If it was in the fourth quadrant, that would be a pushing force. That would be compression. So whenever you see cable, rope, chain, those terms, they're always tension, always. A little bit of background. I think that can get you started with when we do these problems, just to kind of get an idea of what's going on as the terminology. Does anybody have any questions on anything before we get started? On anything I went over there, but again, it'll make more sense when we're doing problems. This new iPad Pro and Apple Pencil, it looks pretty nice, doesn't it? Pretty dope, as the kids would say. A lot of thumbs up on the Apple Pencil. It just makes hard. The only hard thing is I can't see your thumbs up so easy. I got to scroll around. So now I'm in the 21st century. I don't have to type everything out and have all my numbers go over top of each other. All right, let's get started. Today we are doing concurrent force systems. I still can't write very neat. Concurrent force systems in equilibrium. That's today's lesson. And for these, it's always sum of the forces in the x equals 0 and sum of the forces in the y equals 0. Those are the two things you have to satisfy for a concurrent force system in equilibrium. We're always going to have two equations for concurrent force systems in equilibrium. Always two equations, always. And we're not going to be doing any charts anymore, because we're going to solve these out linearly, because we're going to have to use some algebra. So let's try it. Here I have an object and a cable. And I have a force here. I'm going to say this force is 55 newtons. This angle here is 37 degrees. Nope, I got that force backwards, sorry. It's got to go the other way, my bad. So the question would say, what is the weight maximum maximum weight of object if suspended in equilibrium. Is the maximum weight of the object if suspended in equilibrium? That's our question. So we want to draw a free body diagram. So we take our object, and I'm just going to redraw it down here. We have F equals 55. We have a weight. Weight is always a downward force. And we have our unknown. We'll just call that C for cable. And that's at 37 degrees. So to solve this problem, we use our two equations. I'm going to erase the original question because I need some room. Did a bad job of spacing. We have the sum of the forces in the x equals 0, and the sum of the forces in the y equals 0. Those are our two equations. Well, let's look down here. C is made up of C cosine 37 and C sine of 37. C sine of 37 goes up. So let's do the x direction first. We have C cosine 37, 55 minus C cosine 37 equals 0, right? 55 is positive. I'm just going to go over a little view. Negative x, positive y, negative y. So 55 equals C cosine 37. C equals 55 divided by the cosine of 37, 68.87 newtons. That's the force in the cable. So what is the maximum weight that can be supported by this force? Is it 68.67, right? We know that this force right here is 68.67. 87. That is not equal to the weight. The y component of that force is going to equal the weight. Those are the two forces going against each other. So when we do our y, we have C sine of 37 minus W equals 0. C sine of 37 equals W. W equals 68.87 cosine, not cosine, sine 37 41.35 newtons. That is written backwards. How do we do? Do you guys, anybody have any questions on that? If you have a question, let me know. All right, let's take this up a level. Now we have a new problem. We have an object. Let's start over again. We have two, this is a really common problem that we have. In between these two planes, we have a ball stuck in there. And I'm going to give you the angle of these planes. We'll make this one 52 degrees and this one over here, I don't know, 40 degrees. And the question would say, if I could write, find the forces acting on the object if it weighs 700 pounds. Somebody have a question? All right, so we want to represent this. So how many forces are acting on this object? Anybody besides the weight? I'll give you a hint. It's 1, 2, 3, or 0. Other than the weight, how many forces are acting on this object?
2. 3 and
2. Good. 2 forces. Now, let's draw a free body diagram. We have our object. This object has a weight. That's 700 pounds. Now the 2 forces are acting here and here. So, what are the names of those forces? What types of forces are they from our previous lecture talk?
Normal forces.
Normal forces, good. We have 2 normal forces. Now look at the angles they make, right? They don't make 40. This angle here is not 40, and this angle is not 52. Those aren't the angles. Notice this is 52, and we got our little triangle. Let me do this in yellow. That'll be even more exciting for you. We have this little triangle here. We know this angle is 52. This is perpendicular, so that's a right triangle. What does that make this angle?
38.
Right? This is our triangle. Right triangle, 52. This has to be, I think I heard somebody say it, 38 degrees. So the force in our free body diagram, we can call this guy A, acts at 38 degrees. Does anybody need anything clarified? Everybody sees it. Good. Now, let me erase this because of that. Act over here at 50 degrees. Calling this one B. So our goal, find A and B. Now remember from algebra, we have 2 unknowns. How many equations can we have? 2. Good, class. So our 2 equations, sum of the forces in the x equals 0 and sum of the forces in the y equals 0. Well, it's going to be tricky for me to fit this all in this space here. In the x direction, notice our components. I'll draw them right here. We have a cosine 38, cosine 50, a little wanky b sine of 50. So in the x direction, we have b cosine 50 minus a cosine 38 equals 0. Well, we can't solve for either of those, so let's go to the y. In the y direction, we have b sine of 50 plus a sine of 38 minus 700 equals 0. I'm just going to draw a line down through here so it separates the 2. They don't get confused on top of each other.
Can we get like a minute to copy it?
But I'm not going to want that line because... Sure.
And you can make straight lines.
I'm so excited to do these problems.
You can do the straight
just like I
line
did before,
with
right?
a ruler.
Where's the ruler at, girl?
Okay, so like where it gives you all the options, it's like a little ruler. It's so much fun.
A little ruler.
Like with all the pencils, where all the pencils are.
Yeah, pencil. Just give me different colors. Oh, I don't see any pop-ups.
Okay, so like there are different kinds of pencils. Like there's the marker and then the pencil and then some other, like a highlighter or something. And like then there should be a ruler.
I don't see mine aren't coming up. I have to dig deeper.
You'll figure it out.
All right, so let's just solve this problem. I'll find that rule another day. I do need some more fun things to do, though. Someone said I'm lagging. Is that happening for everybody or just that person?
Yeah, it's happening for me.
Me too.
It's happening for 2 people? 3
Yeah,
people?
bad.
Yeah, it's
Bad?
happening for me too.
Me too.
Everybody?
Yeah.
Oh, man. I wonder if this Zoom can't keep up with this iPad. I can't go back to drawing problems on that crazy computer.
It
Hold on, let me
lags,
see what
but like,
network
it's
I'm
like
on.
fine. Like it's just a couple seconds.
It's annoying enough to be annoying, right?
Eh,
Let's try this network. You still there, or did I shut it all down?
We're still here.
Am I lagging still?
I'm not seeing anything getting written.
I kind of got rid of the screen somehow. Now it disappeared. Now I can't get the screen back up. Let's try another screen. That one works. That one works. There's the screen. You see it again?
Yep.
What's lagging, my voice or the writing?
I'm not sure.
Like, is my voice breaking up, or is the writing just behind my voice?
Sometimes your voice breaks up, but it hasn't done it in a while.
All right. Well, if it gets really bad, just yell or something. So now we got to solve for A and B. We got 2 equations. So what we're going to do is set the x equal to each other. So we're going to say B cosine 50 equals A cosine 38. And we're going to make a ratio. B equals A cosine 38 over the cosine of 50. You follow me? Now I'm going to take this and I'm going to substitute it in for B. This is called algebraic substitution. So that gives me A cosine 38 over the cosine of 50 times the sine of 50 plus A sine of 38. I'm just going to take the 700 to the other side. So this is the step that loses people. Is there anybody who needs me to clarify what I just did there? All right, so we're all good. Now I got to get A by itself. So I'm going to factor out the A, right? I'm going to take this A and factor it out. So that's going to give me A cosine 38 over cosine 50 times the sine of 50 plus the sine of 38 equals 700. See how I factored that A out? Now I have to get A by itself. So here we go again. A equals 700 divided by, I'm just going to move this sine of 50 to the numerator. Cosine 38 times the sine of 50 over the cosine of 50 plus the sine of 38. And you can put that whole thing in your calculator to solve for A. So let's try to put it in our calculators just to see if we can. That's a 38. I got A to equal. It's 700 divided by 1.5548. So A equals 450.23. You follow me?
Yep.
Now, are we done?
No.
No, we're not done. We have to find B yet. So I'm going to take this value for A, and I'm going to substitute it back in for this A. So that's going to give me B equals 450.23 times the cosine of 38 over the cosine of 50. B equals 551.94. All right. Any questions there? Anybody have any questions? Anybody? Any chat questions? I didn't see any chats come out. Is everybody caught up? I'm going to do another problem here. Almost identical, but a little different. This time I have an object. I got to move this side some room. I have an object. I'm just going to draw the free body diagram. Oh my goodness, it's a trapezoid. Let's go black. Here's my object. And it has its intention, right? It's being hung by two cables. We'll call them A and B. And we'll put them at, well, let me switch this up just a bit for you, just to make it a little bit more fun. Put it like this. A and B. And we'll put the angles here, I don't know, 60 degrees and 42 degrees. And there's a force in this direction of 3 tons. And we want to find the forces in A and B. That's our goal. Goal. Find tension forces in A and B. So we pretty much have the free body diagram. As you know, I like to draw my components out just so I have them. B cosine 42, B sine of 42, A cosine 60, A sine of 60. So I can see what's going on. I'll give you a minute to catch up with your free body diagram. And now we want to solve this problem. Remember, we have two equations. We have the sum of the forces in the x equals 0, and the sum of the forces in the y equals 0. Those are our two equations. we go up to our picture and we figure out what forces are acting in the X. So we look at our picture, we see, all right, those are our X forces. So I have A cosine 60 plus B cosine of 42 minus 3 equals 0. Well, I can't solve for A and B because I have two unknowns. So now I'm going to go to the Y direction. I have two forces in the Y. A sine of 60 minus B sine of 42 equals 0. Notice this X has the extra variable this time. It has the one we know, the known value, 3. So we're going to start with Y and set up our ratio between A and B in the Y direction. A equals B sine of 42 over the sine of 60. We're going to take this value, plug it in over here for A, and solve. I want you guys to solve this at your seats. I started it for you. I want to see if you can do this algebra. So I'll give you a minute to give it a try. Sorry if you asked any questions. I stepped out for a second. Did anybody ask any questions? Normally nobody ever asks questions, but this time they probably did. All right, let's solve it. We're going to take what we learned for A and plug it in over here, right? B sine of 42 over the sine of 60 times the cosine of 60 plus B cosine 42 equals 3. Pulling the B out. B sine of 42 cosine 60 over the sine of 60 plus 42. Oh, plus 42. Plus the cosine of 42 equals 3. B equals 1.58 for B. Then we're going to take what we learned at B, plug it back in into A. $1.22. And that's it. That's how you solve the problem. Anybody need anything clarified there? How many people got that right? Put your thumb up. Thumbs up. Anybody? Two people? Three people? Couple people? That's not a good start. All right, now we get to try them at our seats. This is concurrent force systems. This is how it happens. This is what it is. Let's try another one. I'll draw this for you. This one you guys are going to solve completely at your seats. Well, I'll start you again because I don't know how strong you are at starting. All right, so that is the problem. Let's see how we do. Give this one a try. Give it a try. With this question, the goal here, I guess I failed to write the goal. Find magnitude of force in A and B. If it were a question in the book, it'd be like in the cables, probably. That's what I would say. All right, so let's look at how to put these set up. We have B cosine 55, B sine of 55. We have A cosine 25, A sine of 25. Sum of the forces in the x equals 0. B cosine of 55 minus A cosine of 25 equals 0. B equals A cosine 25 over cosine 55. Now, some of you may have done A equals B cosine 55 over the cosine of 25. Both are the same, both are okay. All that's going to change is in your next step, when you go to substitute, you're going to be substituting for different variables. So that's our x, beginning of our x right here. Then in the y, we have a sine of 25 plus b sine of 55 minus 100 equals 0. How do we do doing that, getting that far? Did we do all right? Did we get that far? Good. Now solve it the rest of the way out as your seats. Sorry, all you out there in Zoom land. I had this paused this whole time, and I didn't show the steps on how to solve this problem. But here is a picture of how to solve the problem. Just to let you know, this is the tangent of 55. That's what we're looking at there. So anyway, back to where we're at. The next problem is another concurrent force system in equilibrium. It says if the weight of the object is 310 pounds, what are the magnitude of the forces keeping it at rest? Keeping it at rest, question mark. And we're using A on the left side. Our force on the left is going to be called A, and our force on the right is going to be called B. So give this a try. Start to finish at your seats. See how far you can get. I'm going to go ahead and draw the free body diagram. And the weight. I forgot to put the weight on here. So that's what your free body diagram looks like. In the x direction, we're going to say the sum of the forces in the x equals 0. A cosine 60 minus b cosine 20 equals 0. A equals b cosine 20 over the cosine of 60. Then in the y direction, a sine of 60 plus b sine of 20 minus 310 equals 0. I'm going to substitute a in. We'll do it in a different color. So b cosine 20 over the cosine of 60 times the sine of 60 plus b sine of 20 equals 310. B cosine 20 sine of 60 over the cosine of 60 plus the sine of 20 equals 310. $157.39. And I'm going to plug this back in for A and get 295.80. And I found my two values.
Where does the 310 come from?
310 was the weight. It was given in the original
I see that. Thank you.
problem. It's hard to solve without that, right? Anyone else have any questions? I would recommend you do your homework first and then do the quiz. If you're just one of those people that jump right into the quiz, if you picked up on it, it's good. You need a lot of practice. The more practice you can get with this, the best. This is probably the hardest thing in chapter 4, I think. All right, I'm going to stop the recording.